Okay, hi guys, this is video 3-9, see your checklist for when to watch it. And we do have to make a few changes to the problem itself. So the topic here is related rates problems. And you'll see, we'll get to the end of this problem and then I'll explain why it's a related rates problem. But they're actually, students usually have a tough time with them. And when I went to this AP Calc workshop 2 summers ago, we were talking about teaching this topic because it is so challenging for students and challenging for teachers to teach. A few people said that they just cover this particular type of related rates problem, which is a cone problem, and then when the students have more calculus under their belts, they revisit it throughout the year, as more knowledge, as students get more knowledge. So we're just going to do a cone problem, 2 days of cone problems, and then you'll have one on your exam. So water is being poured into a conical tank at a rate of 4 cubic meters per second. Okay, so if you have a rate, you've got to be aware of that, because that's the rate of change of something. That's d something over, in this case it's changing per second, so per time. So d something over dt. If the radius of the tank is 10 meters, and we have to add this in, and the height is 5 meters, how fast, now if they're asking how fast, they're asking for another rate. So how fast or how slow or at what rate, those are clues that they're asking for a rate. So how fast is the depth of the water changing? So how fast is the depth of the water changing when is important, the water is 3 meters deep, okay? So we're being given a rate, they want to know another rate, and then they're telling us when, at what moment. So basically this is a related rates problem. You're given rates, you're asked about rates, related rates. Okay, so or you're given the rate of one thing, and then the rate at which one thing is changing, you're asked to find the rate at which another thing is changing, and those two things are related. So draw a picture of the situation. Do not label the picture with any numbers. So notice guys, I already took away, your page looks different than mine. I have a whole system of tables over there that we're not gonna even use. So yeah, this will be different. So draw a picture of the situation. Do not label the picture with any numbers. Okay, so don't label it with any numbers yet. Okay, so you draw a tank, and there's water that's in it. Okay, to solve the problem, we need to write an equation. To figure out the equation, identify the concept from the box below that is relevant to this problem. So guys, we're just going to deal with cone problems which involve volume, but a related rate problem could really involve any formula. So Pythagorean theorem could be what you're using, area or surface area, perimeter, circumference, trig, the distance formula, similar triangles, any of those things could be involved in a related rates problem. So okay, so we drew the picture. This is volume. I just kind of gave it away. So I'm going to write it down. So the volume, when I'm talking about volume, I mean the volume of the water in this cone. So the volume of the water in the cone is 1/3 pi r squared h. You just have to know that formula. Okay, label the picture with any constant dimensions that were given. I said not to label it right away because you can only label your picture with constants. And by constants, I mean things that are not changing. So they told us that the radius of the tank is 10 meters, so that is a constant. The tank itself is not changing. So I'm going to label that 10. And then the height is 5 meters. That's another constant. All right, so you can only label the picture with constants. Okay, so label the picture with any constant dimensions that were given. Label the picture with the variables in the equation. So this equation, just like I said, this is the volume of what? It's not the volume of the tank itself. That would be like how much water the tank could possibly hold. This is the volume of the water here. And this volume is changing. So that radius is changing, the radius of the water, and also right here, that's the height of the water. Those are not constants, so I can only label them with variables. Okay, now, whenever you're solving a related rates problem, and I'm going slow, guys, because, again, this is a challenging topic, but speed up the video if you want. No, want, what? Went? No, want, when. All right, so I do this, I write down these 3 things because these are the keys to figuring out a related rates problem. What do we know? So essentially, like, what rate do you know? We know the rate, we know that water is being poured into the tank at this rate. So if it's being poured into the tank at that rate, like, all of these variables are changing, V, R, and H, but like, the rate of the water being poured in, that's how the amount of water in the tank is changing. So that's the rate at which the amount of the water in the tank is changing. So, oh, and another clue is that this rate is 4 cubic meters per second. Cubic meters, that's how volume is measured. So that's the clue. Everything I'm saying right now is the clue that you know dV/dt. Okay, dV/dt is the rate of change of the volume over time. So the rate of change of volume over time. As time changes, the volume changes at this rate. I'll just do 4. That's what we know. What do we want? They want us to answer this question: how fast is the depth of the water changing? Well, the depth of the water, guys, we've got 3 variables, V, R, and H, 3 things that are changing. The volume of the water, the radius of the surface of the water, and the height of the water. Well, if they're asking how fast is the depth changing, which of these, V, R, or H, are like synonymous with depth? H. Depth and height are the same thing. So they want dH dt, and when, they will have to tell you a specific moment because time is passing when you're doing these problems. So time is changing. So like at what moment do they want this? When the water is 3 meters deep. So anytime you're encountering like any sort of word problem, I guess, in Calc class, it's not a bad idea to write down a know, want, when chart. All right? Then, so you figure out what formula is helping you. You draw a picture, you figure out the formula that's going to help you. You establish know, want, when, and then you take the derivative. All right, you take the derivative of this. So it's going to be, everything is changing with respect to time. So d whatever dt. So we go d dt of v equals, and I'm going to go super slow. You don't have to go as slow as me when you're on your own, but let's write this down together. All right, so I'm taking the derivative of both sides of the equation. This one is going to be easy. That's just going to be, let me take the derivative of everything like kind of at the same time. This one's going to be easy, so I'll do it a little bit later. I still haven't taken the derivative yet. This one, we need the product rule. And if I were you, whenever you've got constant multiples or coefficients, I usually include those in the first function. And then this would be the second function. So I'm just going to set up product rule. So ddt of the first function, this is like bracket prime. And then I bring down the second function. So this is like bracket prime, kind of. Okay, so there's this. Kind of like I moved the prime inside as a ddt. So think of it that way. Okay, and then plus Now the first function just comes down. 1/3 pi r squared. And then the derivative, the derivative of that one comes down. Okay, so this is like, I don't know that the colors are even helping, but yeah, probably not. Oh well. So it's sort of like, we used to say bracket prime, or how was it? Did we say bracket prime plus, I forget. But I think it was like bracket prime, bracket plus bracket prime. That's the power rule. But instead of having the prime, like instead of having the derivative notation outside, I just put it inside as ddt. Okay, so now I'm going to take the derivatives of these things. So the derivative of this is just 1 dv dt equals, this is just a constant multiple. So 1/3 pi just comes down because it's just a constant that's being multiplied by the variable part. And then 2r dr dt. And then h is just coming down. Okay, so times h, that's just coming down. Plus, this is just coming down 1/3 pi r squared. And then the derivative of this, of h, is just 1, and then dh dt. Okay, implicit differentiation on everything. And then let me just like, okay, so then at this point, guys, I'm going to replace everything. So I want dh dt. So I'm going to leave a blank parenthesis under everything except dh dt. So where do I have a dh dt? Only here at the end. Okay, so this here, I'll bring it down as h prime, but I'm going to leave a blank parenthesis under every other like variable thing. So, and let me simplify that a little bit. That's 2/3 pi blank blank blank, because r dr dt and h, plus 1/3 pi blank squared, that's just a 1. Okay, and then this is just coming down as h prime, just because it's easier to work with. And that, okay, so then I try to plug in for the other stuff. So I leave a blank under every, I got to substitute something in for everything except what I'm solving for. dv dt, do I know that? Yep, it's 4. It's 4 cubic meters per second, but I just put 4 in. 2/3 pi r. Do I know r? No. I know the radius of the cone of the tank, but I don't know the radius of the water, and all of this stuff pertains to the water, so I can't plug anything in for there. Do I know dr dt? No. Do I know h? Yes. This, we're plugging in stuff at this moment in time when h equals 3. Plus 1/3 pi, do I know r? Again, I already said no. So we've got a problem because we don't have stuff to plug in for r. This 2, by the way, went right there. Okay, we don't have stuff to plug in for r or r prime, dr dt. Yeah, so this is when you need a second equation. So we need another equation. And the tricky part about cone problems is that to get the second equation, you need to set up a proportion. So we've really got two triangles, two right triangles here. We've got this one. And actually, the Common Core geometry test, a couple years ago, there was like a problem where you had to use similar triangles with a cone at the end. And I thought, oh my gosh, the Calc kids do that. So right away I knew how to do it, but I don't know. If I didn't teach Calc, it would have thrown me off even. That was kind of a hard problem. Okay, so I've got to go r over h equals 10 over 5. And you could have set it up differently. The proportion is 2 over 1. And then I get that r equals 2h by cross multiplying. So wherever I had an r, I could put a 2h in. So this r here, I can put 2h in there. That was R prime. This R, I could put 2H in there. Now, I still need to plug in for R prime, though. Well, since I've got this second equation, I can do implicit differentiation on it. So the derivative of R is 1, dr dt equals derivative of that is 2 dh dt. Yeah, so I've got that R prime is 2H prime. So I can, R prime. So I can plug that in where there was the R prime right there. Okay, now I've still, that's 2H prime, 2H prime is what I wanted to plug in. Okay, and now I got to solve for H prime, but I still have an H in there, but already I knew H was 3. So this is 4 equals 2/3 pi, H is 3, so that's 6, times 2, and then H prime, 3 plus 1/3 pi, that's going to be 36, because H is 3. Okay, so I can factor out, well, let me clean this up a little bit. So this is canceling with that. Okay, so those are becoming 1s. And then over here, that is canceling. That's going to be a 12 now, and that's a 1. So I get that 4 equals 2 times 6 times 2, that's 24 pi H prime, plus 12 pi H prime. So you get that 4 is equal to, you could combine like terms actually, but I'm factoring out the H prime. So 4 is equal to 36 pi H prime. And then I divide both sides by 36 pi. Guys, this goes a lot faster when you're on your own. I'm explaining it. That's why it's going slow. Shoot. I multiplied them. 4 divided by 36 pi. Okay. So you get that H prime, or dH dt, is equal to 0.0354. AP Calc people, the College Board wants 4 decimal places, at least 4 decimal places. And then I need the units. This is height over time. Height over time. How is height measured? Height in this problem is measured in meters. Meters per time is measured in seconds. So meters per second. Okay, guys. So yeah, let me know if you have any questions. We're just going to focus on cone problems. So today, yeah, we knew that that dVdt was positive 4 cubic meters per second because water was being poured in. Tomorrow, we'll do one where water is leaking. So that will change things just a little bit. Okay, bye-bye.